Hey everyone, Mr. Fransky here. Today we're going to be talking about the mean value theorem, which is an important theorem that AP likes to ask questions about all the time. So today students will be able to decide whether the mean value theorem applies to a function and find the C value if it does. So we're going to talk about what that means. There's a very specific theorem where you're trying to find this value of C. So, vocab. Mean value theorem, of course. Often you'll see that abbreviated MVT. Secant line. We talked about secant lines before. Remember, that's the line that goes through 2 points of a function. Tangent line, remember, is the one where it's going to be just the slope of the function at that point. It kind of bounces off the line. If a function is differentiable, that means we can take its derivative. And continuous means you can draw it without lifting your pen. So let's take a look. So first, this is from our last section, is finding extreme values and where they occur. So we're going to find the extreme values for each one of these and see if we can figure out where they happen. So remember that extreme values can only happen at critical points and endpoints. Critical and endpoints. So what I'm going to do for each one of these is I'm going to list out the critical points and endpoints. Remember, critical points are when the derivative is undefined or equal to 0. Okay, so for this first one, let's see if we can figure it out. So e to the negative x, f prime of x is negative e to the negative x, right? Because of the chain rule, you leave the e to the negative x alone, then the derivative of the baby function is negative 1. So negative e to the negative x. This is never equal to 0, and it's never undefined, because e to the x is always a positive value. So in this case, it'll always be negative, but e to the x can't be 0, right? That's an asymptote for e to the x. And e to the negative x just looks like this. No, neither of them will ever hit the x-axis. So it's never 0, and it's never undefined. So in this case, I'm only concerned about endpoints. So I'm going to have my x values, and then I'm going to have f of x, which is e to the negative x. So my x values are negative 1 and 1. My endpoints, the only things I have to check because I don't have any critical points. So do e to the negative x. So at negative 1, that's just e. At 1, it's e to the negative 1, which is equal to 1 over e. So it looks like our maximum value is e, and it occurs at x equals 1. And our minimum value is 1 over e, and it occurs at sorry, this was negative 1. And this one occurs at x equals 1. Okay? It's been happening a lot lately. I don't know why it's jumping. Okay, so finding these extreme values, just list out all the endpoints and critical points, plug them all in, and see what you've got going. This makes sense to me because e to the negative x, we kind of already drew, it looks like this. So lower values are going to give you higher y values. Higher values of x are going to give you lower y values, right? Why does that keep happening? I don't know. Okay, so next up, we got secant x. Secant x on open parentheses, negative pi over 2 to 3 pi over 2. So the derivative of secant x is secant x tangent x. That's f prime. And let's see if we know when that is 0 between negative pi over 2 and 3 pi over 2. So secant is never 0, right? Secant is never 0. It can be undefined, though. So this is 1 over cosine x times sine x over cosine x. So cosine x, if that's ever 0, we're going to have an undefined moment. So critical points, let's see here. So if cosine is 0 at pi over 2 and 3 pi over 2. So in this case, we're going from negative pi over 2 down here all the way around to 3 pi over 2. So basically, we're going around the circle one time. So the critical point we're going to have here is pi over 2 for sure. So at pi over 2, that's at the top here, cosine is 0. So this whole thing is undefined. And then what else? So pi over 2 is a critical point. And then what else is going to be a critical point? Let's see. Anytime sine is 0 as well, because that's going to make the derivative 0. So 0 and pi are also going to be critical points. 0 and pi. So we make our list here with our endpoints and our critical points. Now notice here we have no endpoints, right? Negative pi over 2 and 3 pi over 2, they're open parentheses. So because we can't quite get there, we don't have endpoints. All right? So let's make a list of our x values. Pi over 2, sorry, let's do them in order, I guess. 0, pi over 2, and pi. Okay, and then we're going to have secant x. Secant of 0 is 1. Secant of pi over 2 is undefined. And secant of pi is over here. That is 1 over cosine, it's negative 1. Okay, now, this might be a little bit misleading, because if we think about this function, it's not continuous, right? So the extreme value theorem doesn't apply, so we really have to think about this. Remember, the secant function kind of touches where the bumps of the cosine happen. So negative pi over 2 is going to be right here. So we're going from here to positive 3. No, I got to make sure I get this right. Negative pi over 2 is right here. sorry, right there. And then positive 3 pi over 2 is right here. So we're doing one full wave of cosine. And the secant function has asymptotes at both of those spots. And it's going to come down like this, and have an asymptote here, and then it's going to have another bump like this. Okay, so it looks like we don't have an absolute max or an absolute min because we go up and down forever. But it does look like we have a relative min. We have a relative minimum at 0, and that's when y equals 1. And then we have a relative max when x is equal to, looks like it would be pi, and y equals -1. Cool. Why does that keep happening? I don't know. Go back. Back again. There we go. Okay. So, next up we got x to the 3/5 on -2, 3. And the -2 is in parentheses there. Okay, interesting. Let's see what happens. So, f prime of x would be, let's see, it would be 3/5 x to the -2/5. So we could rewrite that as 3 over 5 x to the 2/5. Okay. And let's see, so the only critical point in there then, this will never equal 0 because we have a number on the top, and the only way fraction could be 0 is that the top is 0. And this is going to have a critical point, though, when x equals 0. So our only critical point is x equals 0. Okay. So let's see what's going on here. So we make our list, our x, and then our x to 3/5. So we're going to do endpoints to critical points. There is no endpoint on the left because we have an open parentheses there. So 0 and 3 are kind of our critical point and our one endpoint there. So when x equals 0, x to 3/5 is 0. When x is 3, looks like we're going to have 3 to the 3/5, which is the 5th root of 3 cubed, which is 27. So it looks like that's going to be a maximum and the 0 is going to be a minimum. If you graph this, the graph of this, so anytime you have an odd over an odd, it's going to kind of look like the cube root function. So it's going to come up like this. Looks like it's not differentiable right there at 0, which we know because we have this guy right here. So it turns out that's not actually a max or a min. And it looks like, so if we start at -2, let's say -2 is right there. That's going to be an open circle. It's going to be a hole. I'll redraw this so that it comes out of that hole. And let's say 3 is like right here. Oh my goodness. That's going to be annoying. Okay, so 3 would be a solid circle right there. So it looks like we have a max. Come on. A max at x equals 3. And that value is y equals the 5th root of 27. My pen is not working well today. I'll try to fix that for the next video. Okay. And then we have no minimum because it comes to this circle, this open circle here. It comes down, it gets close to that value of whatever the -2 to the 3/5 is, but it doesn't get there. The undifferentiable point here is a vertical tangent, so it's not a maximum or a minimum. Interesting. Okay, let's jump into the mean value theorem. So first I want to talk about what a smooth function is, because to use the mean value theorem, you have to have a smooth function. So smooth just means that it's continuous and differentiable. So smooth means kind of what you think about, right? It means that the function doesn't do anything funky, right? So it's smooth, right? Like that would be a smooth function because there's nothing weird that happens. So things that are no-nos, so no-nos for smooth functions, you can't have any corners, right? Because it's not smooth. You can't draw through it smoothly. It's not differentiable at that corner. You can't have any cusps, right? You can't have any discontinuities. So like a vertical asymptote is no good because you aren't continuous there. And not continuous means you're not differentiable. A jump definitely would not be a smooth function, okay, because it's not continuous at that point. I'm trying to think of other things we talked about. I guess a removable discontinuity. So if you had a hole, that would not be a smooth function. So smooth just means you are continuous and differentiable. So that's our definition of a smooth function. All right, so let's see what the mean value theorem is. So there's kind of this famous drawing of the mean value theorem, and we'll kind of talk it through, and then we'll write out exactly what the mean value theorem says. So if you have a function, let's say your function looks something like this. Okay, and what you do is you take a right here, let's say b is over here. Okay. So f of a would be right here, right? That's just the y coordinate when you plug a into the function, and f of b would be right here. Now, we talked about secant lines before. See if I can draw a decent one. That's not bad. Okay, so the secant line between a and b, remember, just kind of cuts a piece off of the function. So if we want to find the slope of that secant line, the slope of that secant line would be f of b minus f of a, that's the change in y, over b minus a. Okay, now what the mean value theorem says, I don't know if you guys ever, in art class, we had these things called rolling rulers. I don't know if you ever saw them. The ones we had were always like trapezoid shaped. And they had, so this edge over here was like a straight edge, and there were these little wheels, so there was like a kind of a track here, and there were these wheels that went in the direction so that you could roll it up or down, but it would be straight, so you could make parallel lines, right? So like if you want to draw a bunch of parallel lines, you could roll the ruler. So imagine that you put that straight edge right here on AB. If you roll that ruler back towards the top, this bump of the function, what do you think is going to happen? What happens at some point between A and B? Hopefully you can see that at some point on here, you're going to end up with a tangent line that has exactly the same slope as A and B. It's going to be parallel to that line. So what the mean value theorem says is if you have this function where you have this secant line with a certain slope, there is some value c in between A and B, necessarily in between A and B, where the slope of that tangent line is exactly the same as the slope of the secant line. So this is basically mean value theorem. Is if you take the derivative and you plug, there's some c value between a and b where the slope of that is going to be exactly the same as the slope of the line. So here's the slope of the secant line over here. And they're saying there's some c value in between a and b where the tangent line has the same slope. Okay, so this is exactly what it says. So what they say is, this is what mean value theorem says. Mean value theorem. If, hopefully this pen is not going to drive me nuts before we get this all out. Oh my goodness. Okay. So, mean value theorem says, if f of x is continuous on bracket AB and differentiable on parentheses AB. Now that's important, right? It doesn't have to be differentiable at the endpoints, because we talked about that before. Differentiability at the endpoints is kind of weird because you're not thinking about like the values a little bit beyond each side. But it has to be continuous on the closed because we have to get these points to get the slope of that line. But the differentiable just has to be open AB. So if f of x is continuous on AB and differential on AB, so in other words, it's smooth, right? So that's our new fancy keyword. So if you have a smooth function between A and B, then there exists, this is very frustrating, I can't see what I'm writing as I'm writing it. There exists a C on open AB. So that means it's between A and B. It's not equal to A, it's not equal to B. Sometimes you'll have a function like this, right? So at A and B both, notice that the slope would be horizontal. And if you make the secant line, it would also be horizontal. But what mean value theorem guarantees, it's even stronger. There's going to be some point between them where it also happens. So in between, it doesn't have to be at A or B. There's going to be a point in between as well. So there exists a C on AB such that this is true, but I'll write it again. F prime of C is equal to F of B minus F of A over B minus A. I fear this video might get a little long because I'm going to do a few examples of this now, but it's important to take a look at this. So if you, there's also a worksheet. If you guys want to work through the practice problems on the worksheet, I'm also going to make a video of that worksheet. But it's up to you if you want to try these problems or those problems or both. Okay, so let's take a look at some problems. So first of all, I want to talk about why the conditions are important, why it has to be smooth. So the first AP problem I ever gave you was a velocity function. It looks something like this. And they asked a question about, like, here was our A, here was our B. They asked you to find the average acceleration between A and B. So this is the velocity, this is time. Remember, you find average acceleration by finding the slope of the secant line, right? Because that'll be change in velocity over change in time, right? Change in velocity over change in time gives you average acceleration. Right? Instantaneous acceleration happens when you do the slope of the tangent line. So then they asked, is there an instantaneous velocity or instantaneous acceleration equal to that average? So think about that rolling ruler again. If you roll that ruler up, where is it going to stop, like where a tangent point would make sense? It's going to be like right here, right? There is never a tangent that is equal to the slope of that line. Why not? Because that right there is a corner. It's a corner, so it can't have the same slope as the secant line. Okay, so the answer is no, and I would say because v of t is not differentiable, right? Because that's a corner, differentiable, sorry. on AB. Okay, cool. Well, for once, it actually switched when I wanted it to switch. Look at that. Okay, so f of x equals x squared. Does mean value theorem apply for the interval from 0 to 2? If not, why not? If yes, what is the c value that satisfies mean value theorem? Mean value theorem. Okay, so x squared we know looks like this. Pro tip. Oh my goodness. Pro tip. All polynomials are smooth everywhere. Okay, so what I'm going to say here is x squared is continuous and differentiable. Always good to write down what the premises have to be. Okay, so yes, mean value theorem applies. And now what we're going to do is we're going to say, well, 0 is right here, 2 is right here. So what we're going to do is we're going to try to find a point in between 0 and 2 where the tangent line has the same slope as the secant line. So to do that, we first have to find the secant line. So I'm going to try to find f prime of c equal to f of b minus f of a over b minus a. So a few things we have to do here. First thing I'm going to do is I'm going to find the slope of that secant line. So I'm going to do f of 2 minus f of 0 over 2 minus 0. F of 2 is 4. F of 0 is 0 over 2 minus 0 is 2. So that gives me a slope of 2. Okay, so the slope on this side is 2. Now to find a point C in between where the slope of the tangent line is equal to that. So to do that, I have to find f prime of x. F prime of x is 2x. So what I want is I want 2x to be equal to the slope of the secant line, which is 2. We just found that. So what does x have to be? X has to be 1. So that tells me, if I zoom in on this just a little bit, let's say this is our x squared. Here's 2, here's 0. What they're telling me is the slope of that secant line, which I just drew terribly. If you go at 1, you're going to have exactly the same slope. Now with quadratics, it kind of always happens that it's halfway in between. With higher order functions, that's not going to happen. Let's take a look at another one. Now, of course, it doesn't move when I want it to move. There we go. How about f of x equals x to the 4/5 on the interval -1 to 1? So once again, does mean value theorem apply? If not, why not? And if yes, what is the c value? So this is not a polynomial, right? Because this has a root. This is the 5th root of x to the 4th. So the easiest way to find out, so this guy is going to be continuous, right? There's no point where this is not going to work just for an x value plugging in. You plug in 0, you get 0. You plug in -1 to the 4th, that's fine. It gives you a positive number, 5th root. It's going to stay positive. What I like to do is take the derivative to see, to see if it's differentiable. So I'm going to do f prime of x. So that's going to be 4/5 x to the -1/5. Anytime you have a negative, it's suspicious. So we have 4 over 5 times the 5th root of x. Look at this interval. Is there a value in there that is not going to be happy in here? 0 is not going to work well. This is not differentiable at x equals 0. At x equals 0. Now this is important because if 0 was not part of my interval, if my interval was like 3 to 5, this would be fine because it's differentiable everywhere from 3 to 5. But because we have 0 in the middle of this thing, mean value theorem won't work. So it doesn't work. No work. Work. Okay. So, if you want to think about a graph of this, if you graph it on Desmos, I think it's going to be a cusp. Because it's like it wants to be the 5th root. 5th root is like this. But because it's x to the 4th, you have x to the 4/5 here, it's going to force this part to be positive, so it's going to flip it up to the top. That's, I think, what's going on. We have a cusp right at 0, so it's not differentiable. So -1 to 1, you would have a secant line like this, but there's no point down here where there's a tangent line that's the same. Nice. Okay, next up. How about f of x equals x to the 2/3? Now this looks like it's similar, but let's see what's going on. So we're on the interval from 0 to 1. So if we do the derivative, f prime of x, that's going to be 2/3 x to the -1/3. Once again, we have an x on the bottom. That's 2 over 3 cube root of x. And again, it's like, well, we have this 0 here. But what does it say? It's got to be continuous on closed 0, 1. It only has to be differentiable on open 0, 1. Right? And if we're not including 0, then everywhere in there I can plug in, right? I can get as close to 0 as I want, and this will exist, just not at 0. So this is a yes. This one works out. Again, this is going to be a cusp point. But I'm going to be able to find a point between 0 and 1 where the slope of the secant line is equal to the slope of the tangent line. So let's do it. So first, so we need f prime of c equal to f of b minus, f of a over b minus a. I blame the length of this video on my pen not working. Okay. So f of b minus f of a over b minus a. So let's do that first. So we're doing the right side first. So we have f of b, which is 1 to the 2/3, minus 0 to the 2/3 over 1 minus 0. That's 1 minus 0 over 1 minus 0. That's 1. Okay, so we have a slope of 1. Now we have to make the derivative equal to that. So we have 2 over the 3 cube root of x. We want that to be equal to 1. Okay, so let's multiply by cube root of x. So we have 2/3 equals the cube root of x. And then cube both sides. So we have 8/27 equals x. Okay, or c. So sometimes you'll see people, once they take the derivative, they'll put a c in here. In fact, I'm going to do that right now. You don't have to do this. You can do it with an x just like I did, because they're just looking for the number. In fact, this is kind of funny. On the AP test, if you use the wrong variable anywhere, they call it a spelling error and don't take off for spelling. So they're like, well, use the c instead of an x or an x instead of a c. Doesn't matter. Okay, but 8/27 is the spot, so it's going to be somewhere in here. It's less than half, right? 8/27 is where that slope of the tangent line is going to be the same as the slope of the secant line. Nice. Do I have one more? I do. So once again, polynomial, right? So it's smooth. All polynomials are smooth. That's like the keyword, the fancy word you can use for your grader to be like, they know what a smooth function is, okay? So we know, yes, it's going to work for sure, because anywhere for a polynomial, it's going to be fine. So we need f prime of c, c in between -4 and 0, to be equal to f of 0 minus f of -4 divided by 0 minus -4. So f of 0 is 5. F of -4 squared is 16 minus 12 plus 5. So 16 minus 12 is 4 plus 5 is 9. Divided by, let's see, 4, right? So 5 minus 9 is -4 over 4. That's -1. Okay, makes sense to me because we're going from a negative value to 0 and it's a parabola. Yeah, probably a negative slope. That makes sense. So now what we need to do is take the derivative. So f prime of x is 2x plus 3. So now I'll use the c this time. So I want 2c plus 3, because that's f prime of c, to be equal to -1. Now we just solve. Subtract 3, 2c is -4, c is -2. We talked about this before, right? It's halfway in between because it's a parabola. You always want to go through the work, though. Don't ever use that shortcut, but it makes sense to me that it works out. So that means if I graph this parabola, I have no idea what it looks like. Let's say something like this. Here's -4, here's 0. Okay, slope of that secant line is the same as the slope at -2. I'd buy that. If you graph it on Desmos, it'll look a lot prettier, but I'd trust it. All right, finally, we are done. Thank you for sticking with me through this 22-minute video. I love you guys. That's why I'm here. Have an excellent day. I'll see you later.